This video is to support a course that I'm teaching in number theory. This is the 7th video. Last time we talked about the notion of a prime number and proved the fundamental theorem of arithmetic. That is, every natural number has a unique factorization into prime, and that uniqueness is really up to permutations of the primes. Here we're going to start with a very, very classic theorem, and that is there are infinitely many primes. We'll in fact look at a couple of proofs of this just because I like the proofs for different reasons. Okay, so the first proof is maybe the most classic, and this works by way of contradiction. In other words, we'll start by assuming there are only finitely many primes. So suppose all primes are in the following list. So we'll say P1, P2, P3, all the way up to Pn. So here we've got n primes. This is a little n. Okay, so next we're going to form a very important number in terms of getting towards our contradiction. And that number will be the product of all of these primes plus 1. So let's consider capital N, which is equal to this product P1, P2, all the way up to Pn plus 1. And I want to notice the following. So this is a pretty easy observation, and that is capital N is strictly bigger than Pi, and this is going to be true for all I between 1 and n. Well, why is that? Well, notice it's the product of all of these things plus 1, so that's pretty clear. Okay, so that means that this capital N cannot be on this list. Well, why not? Because it's bigger than everything on this list. So in other words, we know that N is not prime. Great. But if N is not prime, and these are all of the primes, by the fundamental theorem of arithmetic, we know that one of these primes must divide N. So let's write that down. So Pk divides N for some k between 1 and n. Again, that's by the fundamental theorem of arithmetic. Okay, but notice that that tells us that Pk also divides the following number by one of our results involving divisibility. And that number is going to be n minus this product P1 up to Pn. You might say, well, why does it divide this product? Because Pk is one of those within that product. And then remember, if you have something that divides two numbers, it divides any linear combination of those two numbers, but that's what we've got here. So just to reiterate, Pk divides n. That's like by the fact that n is not a prime, and these are all of the primes. And then Pk defines this product just by the definition of divisibility. Okay, but now let's calculate this number right here. Notice that this number right here is exactly equal to 1 given the definition of capital N. So that tells us that Pk divides the number 1. But there's only one natural number that divides the number 1, and that is 1 itself. So we've got Pk is actually equal to 1. But 1 is not a prime. Remember that natural numbers are separated into primes, composite numbers, and units. Well, there's only one unit, and that's the number 1. So we've got that Pk is not a prime, but over here we assumed that it was a prime. So we've reached our contradiction. You might say, well, what did we contradict? Well, we go all the way up to the start of this proof, and our assumption was that all of the primes are on the following list. But that means that there are primes that are not on this list. In other words, there must be infinitely many primes. Okay, so now that we've got this, let's go ahead and look at our second proof. Okay, now we're going to look at a second proof. I kind of like this proof more. I don't know if it's just because it's non-standard and Now we're ready to look at our second proof. So it will again be by way of contradiction, and it will start with the same assumption that will contradict here. So in other words, we want to suppose there are finitely many primes. And again, if there are finitely many primes, then that means that we can list them, and we'll list them the same way, P1 through Pn. Now we're going to consider the following kind of interesting number. And that number, I'll call it capital M because we've already used capital N, and it'll be the following product. 1 over 1 minus 1 over P1 times 1 over 1 minus 1 over P2 times all the way up to 1 over 1 minus 1 over Pn. So it's going to be that finite product. The important thing is that that is a finite product. But now we can use the standard formula for the sum of a geometric series to write 1 over 1 minus u as 1 plus u squared, and so on and so forth, and apply that to each of these parts of the product. So we've got this is 1 plus 1 over P1 plus 1 over P1 squared plus ... all powers of 1 over P1. And similarly here we'll have all powers of 1 over P2. So we'll have 1 plus 1 over P2 plus 1 over P2 squared, so on and so forth. And this product will continue until we hit 1 over Pn. So we've got 1 plus 1 over Pn plus 1 over Pn squared plus all the way up. Okay, but now notice if we were to just expand this entire product, we would get exactly the harmonic series. So this is going to be equal to 1 plus 1/2 plus 1/3 plus 1/4 plus 1/5, and so on and so forth. So how do we know that? Well, that's by the fundamental theorem of arithmetic. So we could pick a natural number, and the reciprocal of that natural number is only created by one term from this huge product. Okay, but let's see what we've got here. We've got this number m is a finite product of positive numbers. That means it's a finite number, but it's also equal to the harmonic series. So what did we just do? We just proved that the harmonic series converges. But that's a problem because any Calculus 2 student, well, at the end of Calculus 2, knows that the harmonic series does not converge. So that means we've reached a contradiction. And what did we contradict? Well, going up to the beginning of the proof, we contradicted this assumption that there are finitely many primes. Okay, so now that we've got this taken care of, we're going to look at a couple more results. So one thing that we noticed in our last proof, or our last proofs, was that those proofs were not constructive. So what I mean is that we proved indirectly that there are infinitely many primes. And we did it that way because there's no real constructive proof for the fact that there are infinitely many primes. If there was, then there would be a nice way to construct new primes from old primes, and that kind of thing doesn't exist. On the other hand, there is a way to construct an arbitrarily long list of consecutive composite numbers. So what do I mean by that? Well, let's notice that if we take 8, 9, and 10, those are 3 composite numbers in a row. And you might ask yourself the question, is there some sort of upper limit for how many composite numbers that you can have in a row? And in fact, there isn't, and that's what this claim will prove. So let's look at the careful statement here. So for all natural numbers n, there is a list of n consecutive composite numbers. And as I alluded to, this is going to be a constructive proof. So what we'll do is we'll just construct a list of n consecutive composite numbers. Okay, so let's do it. So let's maybe fix our n, which is a natural number. And now we can just like make a list of n consecutive composite numbers, and we can do it in the following way. We'll take n plus 1 factorial plus 2. Well, let's notice that n plus 1 factorial will definitely be a multiple of 2, because since n is a natural number, that means n plus 1 is definitely bigger than or equal to 2. So that means we can write this as 2 times something. I'll just write it like that. And that's because this is divisible by 2 and this is divisible by 2. And now we can just keep playing that game. We'll take n plus 1 factorial plus 3. And then if n is large enough, n plus 1 factorial is divisible by 3. So that means we can factor a 3 out. And then likewise, n plus 1 factorial plus 4 can have a 4 factored out of it, as long as n plus 1 is long enough. Obviously, this list is not going to last forever, so we really want to think about how long it will last. And it will last up until we're adding n plus 1. So notice n plus 1 factorial is definitely a multiple of n plus 1, and so is n plus 1. So that means we can factor an n plus 1 out of this, and then we have something left over. But now let's count up how many we have on this list. Well, we start at 2, we end at n plus 1. So that means we've got a total of n elements in this list. And we've written all of them in a factored form, meaning that they are all composite. Our next little claim that we'll prove will give evidence towards the fact that it's hard to generate prime numbers. And in fact, what we'll do is show that there is no polynomial that will always generate prime numbers. So more carefully, we could say that like this. There is no non-constant polynomial f of x in z adjoin x. So what I mean by that is f has coefficients that are integers, such that f of n is prime for all natural numbers n. Okay, so let's maybe see how we can do this. Again, we're going to do this by way of contradiction. So this is like a really... So proving things by way of contradiction is a really powerful tool, as we'll see moving through this course. Okay, so let's start off by supposing that there is some f of x in z adjoin x. In other words, a polynomial with integer coefficients, such that f evaluated at n is equal to some prime. I'll just say f of n equals a prime for all natural numbers n. Okay, so what does that mean? Well, the number 1 is a natural number, so that means f evaluated at 1 is a prime. So I'll just say f of 1 equals p, a prime number. So we'll give a name to f evaluated at 1. And now next, we want to look at the following difference of values of f. So we'll look at f of 1 plus m times p, sort of m times p for obvious reasons, minus f evaluated at 1. So let's see what we get for this. So that's going to give us this sum as k goes from 1 up to n of ak 1 plus mp to the k minus this sum as k goes from 1 up to n of ak. And so here I've kind of built into this notation that f of x is equal to this sum as k goes from 1 up to n of akx to the k. So that's just like a standard way of writing a polynomial down in summation notation. Now let's see if we can simplify that. So I'll start by combining those two sums together. That's going to give me this sum as k goes from 1 up to n of ak times the quantity 1 plus m p to the k minus 1. So again, I just pushed those two sums together and then factored the ak out. But now I can take this binomial, 1 plus mp to the k, and expand it using binomial coefficients, and so I'll have a sum within a sum. So just to write that more carefully, I've got this sum as k goes from 1 up to n of AK. And then inside of that, I'll have the sum as L goes from 0 up to K of K choose L, M to the L, P to the L minus 1. And I'll put this sum in parentheses just to show that my minus 1 is happening outside of that sum. Next, I want to notice that at the L equals 0 spot, I've got K choose 0, which is 1, M to the 0, P to the 0, which is also 1. So that's going to cancel out the 1 that's out here. So that'll cancel this starting point from L equals 0 to L equals 1. So that means I can rewrite this as the sum as K goes from 1 up to N. And then inside of that, we have the sum as L goes from 1 up to K of AK, and then K choose L, that's a binomial coefficient, M to the L, P to the L. Now, a little tricky thing that happened here is that we never had to consider the K equals 0 term. That's because that canceled out at this stage right here. Notice the K equals 0 term is the constant term of the polynomial, but whenever you take a difference like that, that constant term will cancel. So what does that mean? That means that every term in the sum has at least one power of the prime P. But that means we can factor out a P from every term in this sum, and that leaves us with P to the L minus 1 on the inside. So let's just talk our way through it. A sub K is an integer. K choose L is an integer. M to the L is an integer. And then P to the L minus 1 is also an integer. Again, that's because L starts at 1. But that means that this whole thing right here is an integer. So maybe we'll replace it with capital M just to notate that that's an integer in the end. So we have this is equal to capital M times P, where capital M is an integer. So let's see what we've got so far. We have F evaluated at 1 plus MP minus F evaluated at 1 is equal to this capital MP. But let's recall that this F evaluated at 1 is equal to P. So we can rewrite this equation as follows. We can write F of 1 plus little mp is equal to P plus capital MP, which is equal to P, and then 1 plus capital M, just factoring the P out. But let's recall that F evaluated at n is supposed to be prime for all natural numbers n. But what we have is that this prime divides F evaluated at 1 plus MP. But now F evaluated at 1 plus MP is most definitely not a prime unless m is equal to 0, and this cancels down just to 1. And in that case, this is equal to just the prime P. So that means we've got infinitely many values of our polynomial is equal to our kind of starting prime P. But if infinitely many values of our polynomial is equal to the starting prime, then that means that our polynomial was constant from the start, but that contradicts our assumption up here that this is a non-constant polynomial. Okay, now that we've gotten this taken care of, we're going to look at some special types of primes. Okay, for our next little result, we're going to look at something called that Fermat prime. And Fermat primes are of the form 2 to the 2 to the k plus 1. And what we'll prove is that if 2 to the n plus 1 is prime, then that means either n is equal to 0 or n is a power of 2. But n being a power of 2 is equivalent to showing that the only prime factor of n is the number 2. Okay, so let's get to this. So we're going to prove this via a contrapositive. So in other words, we're going to assume that n is not a power of 2, and we'll show that this object is composite. So let's suppose that p divides n, and p is equal to some odd prime. Okay, but if p divides n, that means we can write n as m times p. But now let's look at 2 to the n plus 1, which can now be written as 2 to the m to the p plus 1. But this has a standard factorization. And maybe just think about the factorization of the following object. X to the odd number plus 1 will factor as x plus 1 times a bunch of other stuff. So just replacing x with 2 to the m, that means we can make this factorization. This is going to factor like 2 to the m plus 1 times 2 to the m times p minus 1 minus 2 to the m times p minus 2, all the way down to plus or minus 1, kind of depending on the parity of m. And that's going to extend all the way down to just plus 1. So notice that this is most definitely composite because it's been written as some number, which I'll say right here is a, which is bigger than 1, and then some number, which I'll say right here is b, which is bigger than 1. So if it's composite, it is not prime. So we finished this proof by the contrapositive. Now I want to point out again that these are called Fermat primes. But not everything of this form is prime. So you can actually show that the number 641 divides 2 to the 32 plus 1. But I guess I should say that 2 to the 32 plus 1 is not equal to 641. So that'll mean that 2 to the 32 plus 1 is not prime. Okay, so we've got one more claim to prove that involves special types of primes. So our next result will involve Mersenne primes. This is a very famous family of prime numbers, and they are of the form 2 to the n minus 1. We're going to prove the following claim. If 2 to the n minus 1 is prime, then n is prime. And we'll do that by the contrapositive. So the contrapositive reads, if n is composite, then 2 to the n minus 1 is also composite. Okay, so let's maybe get to it. So let's write n as a times b, and then we can consider 2 to the n minus 1, which is 2 to the a to the power b minus 1. Now we can use a similar factorization formula that we saw before. So this is going to factor like 2 to the a minus 1, and then 2 to the a times b minus 1 plus 2 to the a times b minus 2, all the way down to 1. So that proves that 2 to the n minus 1 is composite. That finishes the proof of this claim, again, via the contrapositive. And next, we'll notice that the converse of this claim is not true. In other words, it's possible to have a prime, n, well, we'll call it p, such that 2 to the p minus 1 is not prime. So let's look at our example. So 2 to the 11 minus 1. Well, 11 is most definitely a prime, but this is equal to 2047. But 2047 factors like 23 times 89, which means we've got an example where this thing is prime, but this thing is composite. Again, giving a counterexample for the converse of this claim. Okay, so we're going to finish this video off with looking at some very famous conjectures involving primes. Okay, now we're going to look at a couple of famous conjectures involving primes. So the first is, are there infinitely many Fibonacci primes? So what I mean is that, are there infinitely many primes that are also Fibonacci numbers? Next, are there infinitely many primes p such that p plus 2 is also prime? So these would be called twin primes, and this is famously known as the twin prime conjecture. There's recently been a lot of activity towards this conjecture, and at this point it is known that there are infinitely many primes such that p and p plus 246 are both primes. Next, are there infinitely many Sophie-Germain primes? And so those are primes p where 2p plus 1 is also prime. Then finally, the Goldbach conjecture. and that is, can every even number be expressed as the sum of two primes? So obviously this is not an exhaustive list of conjectures about primes, but these are four that are kind of easy to understand at this stage in the game. Okay, let's get rid of this and then we'll look at some warm-up problems. So we're going to end with a couple of warm-up problems, and these are built off of some of the tricks that were used in the proofs of this video. So first, factor the following two numbers into primes. So 2 to the 24 minus 1 and 2 to the 15 minus 1. So again, like I said, that factorization or those factorizations will use factorization tricks that we had in some of the proofs. Then next, find all primes of the form 2 to the 2 to the n plus 5. So since the question is to find all primes of this form, there's probably some obvious reason why for sufficiently large values of n, you no longer get primes. So what I would do is I would make a list of numbers of this form, and then notice that that list is no longer prime after a certain point, and then let that motivate your proof. Okay, that's a good place to stop.